Good morning. So today, in the previous two topics, we learned massive IoT. Now, in this talk, so we are going to learn about critical IoT. Critical IoT is ultra reliable, low latency communication. So, if you take 6G, it is a new use case, massive ultra reliable low latency communication. If you take 5G, only ultra reliable low latency communication. Here, a new use case, massive connectivity. So therefore, the three requirement together: massive connectivity, reliability, and low latency. Three requirements together. So to achieve these three requirements, we are going to see what are the potential solutions. So one solution is grant free. So to reduce the latency, so here one solution is grant free. So here if you take normally if you take grant based, the 4G grant based, so the base station initially broadcast the system information to all IoT devices. Then IoT device send the preamble transmission. Then base station send the random access response for this preamble. Then it requests connection. So if this agreed, then send the connection request. Then contention resolution. Then only data transmission. So if you take the time taken, so user equipment, this IoT device wait for the control channel, normally 5 millisecond waiting time. Then scheduling request, 1 millisecond it will take. Then scheduling grant, it will take 3 millisecond. So base station send, it is 1 millisecond. Then 3 millisecond, then, so if you take here, you are going to have more than 10 millisecond. But here now the requirement is less than 1 millisecond. So if you use grant based, so you need at least 10 millisecond to transmit the data, to start the transmit the data for the handshaking process. So it takes 10 millisecond. So now we don't need this, we want 1 millisecond, so therefore we are going to remove all these things. So that's the motivation of having grant free. So here, what are the procedures? Acquisition, 5 millisecond. So random access, so normally 9.5 millisecond. So here, to avoid all these handshaking process, so if you take the LT release 8, the uplink downlink, so these are the required time for all the processes. So now this slide I put earlier. So here we are going to remove everything here up to this. Here we are going to remove everything. So by that way we can save 10 millisecond. So whenever a packet arrives, so it is going to transmit the data to the base station straight away. So if you transmit straight away, what will happen? You are going to have collision. Because everybody immediately transfer, collision will occur. If collision will occur, then what will have to do? You have to retransmit again. Again and again. So then also time will consume. So how to avoid the collision? So in the 3GPP release 16, they have proposed some other scheme to reduce the collision in addition to this grant free. So the second solution for reliability, we are going to repeat the same packet again and again. So if you take one packet, same packet, if you repeat 5 times, at least one time it will succeed. even if it failed the remaining, so then it will be considered as succeeded. So now the question is, if you repeat again, so repetition factor, if it is high, so if you repeat 10 times, 15 times, so then again you are going to waste the resources. So now we have to find what is the optimum value of the repetition factor. We have to reduce the repetition as low as possible. So here, when you take the reactive, the hybrid automatic repeat request, so here if you take user requirement is going to transmit to the base station. So base station, the first initial transmission failed. Then it takes the acknowledgement, so not received. So then second attempt, repeat again not received. Third time you repeat, then it acknowledged. So you are going to repeat again and again till you get acknowledgement. So we received. So this is the reactive scheme. Another scheme is the K repetition scheme. K repetition scheme. So you are going to repeat K times. Say for example, 4 times you are going to repeat. Same packet you are going to repeat 4 times. If you repeat 4 times, the base station, it is going to decode independently. Every time it will decode. First time decode, second time decode, third time decode, fourth time decode. At the end of the fourth frame, so it will send the acknowledgement whether succeeded or not. So decode first frame, decode second independently, third, fourth. If one of these one is succeeded, it says that okay, succeeded. But the problem is, for example, if the second one is succeeded, so to get the acknowledgement, it will have to wait 2 more slots, because acknowledgement will be only at the end, not at the end of every time frame. So that is again here we have the disadvantage. If you overestimate the value of K, you are going to waste the resources. We don't know K should be 4 or 10 or 5, we don't know. So because of that, here we have another scheme, proactive. Proactive means, say here, for example, so a repetition, say up to, say here 8 repetition, for example. If you have 8 repetition, here, so first one decoded. If it is succeeded, then no need to repeat again and again. So that means acknowledgement at the end of every packet. So every transmission time. First one, so not succeeded. Second one, not succeeded. Third one, succeeded, then we don't need to repeat again. So but the difference between K repetition and proactive repetition is K repetition send the acknowledgement at the end of the last repetition. But proactive one, so after every frame, so once it succeeded, then terminate. No need to repeat again and again. So here, the problem here is, so user equipment has to monitor the feedback after every time frame. So it is computationally heavy for the user equipment, because user equipment, it will have to process after each frame. So now, third solution. So first one, grant free to reduce the latencies, to improve the reliability, K repetition or proactive. This is for massive connectivity, as I mentioned earlier. So the non-orthogonal multiple access, you can use the same resource block by many users. So using the principle of, so here user requirement 1, user requirement 2. So if you use the same resource block, so and if you use the superposition, pre-coding, and successful interference cancellation like we learned in the second topic. So we can increase the connectivity. Okay, so if you summarize all these three, so grant-free NOMA, grant-free reduce the latency. So the repetition scheme to increase the reliability. Non-orthogonal multiple access, so for massive connectivity. So here we can achieve all three objectives. So that is massive, ultra reliable, low latency communication. So by having grant-free NOMA with repetition, so we can achieve all three requirements. So now another solution, the fourth solution. So now we had the grant-free, then the repetition, and non-orthogonal multiplex. Now fourth solution, so that is so in 3GPP release 16, so 3GPP release 16, so that is 5G. So they proposed multiple configuration grant. What is meant by multiple configuration grant? So here, if you take here, so interval 1, the repetition factor is 4. So that is, the packet is repeated in the interval 1 4 times. So in interval 1 it is repeated 4 times. Now the question is, so in the user equipment, packet arrived not at the beginning of the second interval, but packet arrived in the middle here. In the middle second packet arrived. So what the user equipment can do, it can repeat only 3 times, cannot repeat 4 times. So here third packet arrived here in the middle. So third packet can repeat only 2 times, because if you repeat 3 times, it will interfere with other interval. So therefore, so here in this single configuration grant, so we are going to have only one configuration grant. So that means, so here we have this interval 1, interval 2, interval 3. If at the beginning of the interval, if the packet arrive, fine. So you can utilize the whole interval for repetition. If the packet arrive in the middle, so it can use 3 or 2 or 1 repetition, because you cannot go to the next interval. So that is single configuration grant. So here we are going to have less than 4 repetition, less than K. So that's what in 3GPP release 16, they proposed different configuration. So different configuration is, the first configuration, so the intervals are defined. This is first configuration 1, first interval, second, third, like this. So if a particular for user equipment, if the packet arrive here, it will select this configuration. So if packet arrive in the middle of this one, so it will take configuration 3, because configuration 3 starting time, interval start only here. But here interval starts only one fixed place. But here we have different configuration with different interval start time. So therefore, so what is going to happen? So it will select a particular user equipment. Okay, now so different configurations available. So when the packet arrive in the, say for example, one packet arrive here, so it will select configuration 4. It won't select configuration 1. So if when the packet arrive in the middle, it is going to select configuration 3, not configuration 1. If it select configuration 1, it can repeat only 2 times. So if it select configuration 3, it can repeat this because configuration 3 interval start from here to here. So it can utilize the repetition of 4. So that is what multiple configuration grants has been proposed in the standard release 16 5G. In the 4G only single configuration grant. So now you can see here, so the user equipment, it can choose the correct configuration with the correct starting point to transmit the data. So one user equipment might have multiple configuration grant. So for a particular user equipment, so this is one user equipment. It can have 4 configuration grant. It can select whichever one, because in this smart meter, we don't know when the packet arrives. On the sensor, we don't know when it arrives. According to the arrival time, it can choose the suitable configuration grant. So if you have more configuration grant, it would be better. So because, say for example, if you have 8 configuration grant, so that means one interval. So you are going to have 8 slots. So that means, so during this interval, whenever a packet arrives, it can select the suitable configuration grant and transmit. So no need to wait, because if you have only single configuration grant, so now if you have only single configuration grant, say if the packet arrives here, this is the waiting time. So without waiting, it can select another configuration grant starting from here. So it can choose this one. So no need to wait till this time. So by this way, when you have multiple configuration grant, we don't need to wait. Immediately select suitable one and transmit. So now you take here. So to reduce the latency only, this multiple configuration grant proposed to reduce the latency, to avoid the waiting time. Say here, if you take, so if you have only one configuration grant, if user equipment 2, if it arrives here, if you have only single configuration grant, it will have to wait till the beginning of next interval. Because only one configuration grant you have. You cannot transmit in between. So you have to wait at the beginning of this. So waiting time this one, if you have only one. So user equipment 3, it will have to wait this one. So to avoid the waiting time, this multiple configuration grants proposed. Then, so here, if you have more configuration grant, it will, so user equipment select the configuration grant where the interval start here. User equipment 3 select the configuration grant where the starting time is this one. So by that way, we can reduce the waiting time. If you have single configuration grant, you have to wait till the beginning of next interval, no choice. Sorry?
I mean, users being catered.
Users of? Say here, say for example, if you have 8 configuration grant, so if you have 8 configuration grant, so all users are going to use that 8 configuration grant. So there is a possibility for 2 users to collide, because user 1 also select configuration grant 4. User 2 also take configuration grant 4. But to reduce the interference, that's what we use the NOMA. So by using NOMA, 2 configuration grant can be utilized by the same user, the 2 users, more than 1 user at the same time. So the main purpose of this multiple configuration grant to remove the waiting time. So select suitable one and transmit. So, so this is the motivation of having the multiple configuration graph. Another solution is the solution 5. It is to use because here we are going to have the numerous new applications, augmented reality, mixed reality, virtual reality. So here we have the shortage of licensed spectra. So another potential solution is to use the unlicensed spectrum. So unlicensed spectrum like Wi-Fi spectrum can utilize like cognitive radio, utilize without interfering the other networks. So using low power. So because if you take ISM band, so you have Bluetooth, Wi-Fi, everything you have in ISM band without interfering others. So that is another opportunity. So now here for 6G massive ultra level low latency communications. So in the current research, some are in the standard, some proposed. There are 5 solutions in the standard proposed or in the literature. So one is grant free, other one is multiple configuration, the reliability repetition, then to avoid waiting the multiple configuration grant. So to use the same resource block, nano multiple access. So to increase the capacity, utilize the unlicensed band. So these are the all possible solutions in 6G massive ultra reliable low latency communication. So now we are going to see where we can apply the again machine learning here to improve the performance. So here we are going to see how we can use the machine learning to achieve the latency of less than 1 millisecond. So if you don't use the dynamic optimization, if you use the static optimization, we may not be able to achieve the requirement of less than 1 millisecond. So now we see where we are going to use the machine learning. So for grant free NOMA. So here in the lecture notes, there are 4 contributions. So I skip the first one that is not related to machine learning. Second and third are related to machine learning. So here, as I mentioned earlier, so with the grant free, we can have NOMA together. So by that way, we are going to have same physical resource block utilized by more than one user. So at the receiver, we are going to have successive interference cancellation. So here I mentioned the requirement here. So now the problem is, so we are going to have set of active users. So the base station unknown the channel conditions, because when you have massive connectivity, thousands of devices, so base station cannot estimate the channel of 1000 IoT devices. So here the problem is channel state information is unknown to the base station because of massive connectivity. Then, so here we have to satisfy 2 constraints. One is reliability constraint, other one latency constraint. So latency constraint is the latency should be less than some threshold. So that's one constraint. Then reliability constraint, the probability of error should be very small. So the packet error probability or bit error probability less than very 10 to the power minus 4 or minus 5. So here another problem is, so we have to consider the the collision detection, the user activity detection. So everything we have to consider. So now the question is, so here we don't have the mathematical framework. So here, so this is what in the uplink Grand Prix NOMA, this is what happening. First one, here first in Grand Prix NOMA. So first the packet arrive. So once the packet arrive, base station broadcast the resource parameters, everything configuration done second. Third one, so here latency check. So that means you already set a latency constraint. So because of the collision, if the time exceed the latency threshold, assume that packet is failed. So here, if this latency constraint is not met, then assume that packet dropped. So it's failed. So because it have to the transmission should occur successfully within that latency constraint, within that few milliseconds. The next check, we will see what is meant by CTU. The next slide. What is meant by CTU? Contention Transmission Unit. We will see that. So two CTUs. So same user select. One CTU selected by 3-4 users. Then collision will occur. So then, that also packet drop. Then this succeeded. Then final one. So here at the receiver we are going to have successive interference cancellation. So if that one fails, so then no acknowledgement. So all these satisfied only, so acknowledgement will be sent. So latency constraint, so collision detected, successive interference cancellation done perfectly, then only acknowledgement will be sent. Now we will see what is meant by contention transmission unit. So you are familiar with the LTE resource block. LTE resource block. So here one resource block, 180 kilohertz. Here 1 millisecond. One resource block. So here contention transmission unit means, so with every resource block we have a signature sequence. So third domain is a signature sequence. So it's a signature to identify the resource block. You have physical resource block. So identify, so we are going to have a tag. So that is the signature sequence. So therefore, here we have for the resource block, time frequency domain 180 kilohertz 1 millisecond. In addition, we have a signature sequence. So that is called contention transmission unit. So here we are going to have numerous contention transmission unit. So contention transmission unit means the resource block, you have a identification tag. So CTU1, CTU2, because all are 180 kilohertz 1 millisecond block, the time frequency resources, we have a tag. That is signature sequence. So we can have CTU1, CTU3 like that. So now here you have, say for example, 50 CTUs you have. So these 50 CTUs, so users are going to select one of this and transmit. Now the question is, so here they take the CTU and they are going to transmit using the either K repetition scheme or proactive repetition scheme to increase the reliability. So the CTUs are going to be repeated certain number of times. So they can use, as I mentioned earlier, they can use either K repetition scheme or proactive scheme. So both are recommended in the 3GPP standard. Now the question is, the collision, how it occurs. So you can take one resource block. This is one resource block. You have 3 signature sequences. So then you have 3 CTUs. You take another physical resource block. So 3 signature sequence. So you have 3 CTUs here. So here you have, for example, you have 6 CTUs. So now here you have 8 user equipment. 8 equipments are there. They are going to select one of the CTU and repeat and transmit. Now the question is, so here user equipment 4 and 7 selected CTU 1. So collision will occur. So here CTU 2, 3 and 2 selected, the collision will occur. So here this CTU is idle, nobody selected. This CTU only 1 and 5 selected. So there are 3 categories we are going to have. One is ideal CTU, no one selected that CTU. Other one singleton, only one user selected the CTU. The third one, more than one user selected the CTU. 3 scenarios we are going to have. If we have these 3 scenarios, so as I mentioned earlier, so here we are going to repeat again, K repetition. So if you at the, so here, so one CTU selected by more than one user, then we use the non-orthogonal multiple access. So then what we are going to do? So here we are going to use the successive interference cancellation and decoding here. So then we subtract and decode the second signal according to the power level, like we did. So now this is the K repetition scheme. You are going to decode all repetitions. Then the acknowledgement at the end if one of the repetition is succeeded. If it is proactive scheme, as I mentioned earlier, so if one of the repetitions succeeded, it will be terminated, no more repetition. So by that way, proactive can reduce the latency than repetition scheme. Now we are going to, in the machine learning, we are going to formulate the problem here. So what is the problem here? Like we did earlier in narrowband IoT, we are going to have observation up to, at the particular time interval t, we are going to have observation. Observations mean in the previous time interval, certain time interval. So how many preamble were idle, how many collided, how many singleton, how many devices successfully decoded. All these observations we are going to have. Then at a particular time we are going to select the action. So what is the action that we are going to select is the repetition factor and the number of CTU, because CTU is expensive, because spectrum is expensive. CTU means resource block with a signature sequence. So if we have 1000 CTU, no problem, because 100 users can select one of the 1000, collision will never occur. But the problem is we cannot have 1000 CTU because every CTU 180 kilohertz. So you are going to waste the whole spectrum very expensive. So therefore you are going to select the CTU, whatever the minimum required, you are going to select it, because the remaining spectrum you are going to utilize for some other purpose. You can't take the whole spectrum for this application. There are many other applications you have. So therefore, you have to, at the beginning of every transmission time interval, you have to dynamically adapt the number of CTU, because otherwise waste the resource. Then other parameter, that is going to be the repetition vector. So repetition vector, you have to be as minimum as possible. Then the constraint here, you have the latency constraint you have. Latency should be met and reliability also should be there. So with this optimization problem, so here we consider the weight for future reward. So this is the successfully served devices. This is for future reward. That this is similar to that what we learned earlier. So now this is like earlier. This is a Markov decision process because here we have slots. So base station organizes the transmission, retransmission. So base stations receive the, after each slot, it observes number of succeeded, number of CTUs idle, number of CTUs collided, everything at the end of the slot. At the end of the slot, it observes. Then at the beginning of next time frame, it dynamically changes the parameter base station. So now, so here why it is partially observed Markov decision process, because base station, it does not know the new traffic generation. It does not know base station, because new traffic generation is suddenly at the next time interval, suddenly the devices, number of devices increase from 100 to 300. So 100 to 500 base station, it does not know, because at the beginning it suddenly changed. So this is partially observed. Then collision process unknown. So base station does not know how many people selected one CTU. Because of that, it could not decode. Because more users selected, then SIC also failed. So base station, it does not know. So then it does not know the packet dropping, because if the latency constraint is not met or collision occurred, packet drop, all these details, base station does not know all the details. So it observes only partial observation. Based on the partial observation, it is going to make the decision, action. So here, so base station is going to change repetition value and number of CTU at the beginning of each time slot, such that the reward will be the more IoT devices under latency constraint for long term. So here infinity means future huge number value. So there, but if you take the conventional solution, so conventional load estimation based approach, it optimizes only the single parameter, not more than one parameter. It optimizes single parameter without considering the future. Here we consider the future, here this one future. Here no future during the current interval, but is the load. Okay, load increase, so increase the CTU. Okay, so here the many packet dropped, so increase the latency. So only one parameter is changes. It does not consider future. Future means after 100 time slots, so we have to maximize. So because after 100 slots, the next future 100 is going to be the state, so it will affect. So the current one, conventional one, they do not consider the future. So now, so here, these are the observations we are going to have. If you take the load estimation based the uplink resource configuration, so only for single parameter, estimate the last collision and idle CTUs, and just select one parameter based on the load estimation. So the load estimation is, we learn the method of the moment matching. So that way, so the parameters are optimized in the conventional one. But here we are going to observe the past, so this is the state. So at a particular time interval t, t minus 1 up to last m time slot. So what are the action taken? What are the observations? This U observation action. So here, so you know the deep Q network. So we can update the Q value and the agents make the decision by exploration and exploitation. So exploitation means they make the decision based on the Q value, which action give high Q value, it takes the decision. So here cooperative, because all agents, they cooperatively optimize the objective to increase the number of devices successfully served. So here, these are the observations, 5 observations. How many CTUs collided? How many idle? How many CTUs were singleton? So number of user equipment, they have successfully detected, but when they do the successive interference cancellation, they failed, or they didn't meet the latency constraint, so it failed. So detected fine, CTUs were successfully detected but not decoded. This one detected and decoded. So these are the 5 observations here. So during the current time, at the end of the one time interval, the base station agents observe and take 2 actions. The 2 actions, they are going to, at the beginning of the next transmission time interval, they are going to broadcast the new value of number of CTU and what is the repetition value. So then the base station broadcast, then the user equipment select that value. So then by that way, we can maximize the reward. The number of successfully served devices could be maximized. So here 2 agents here we have. So in the narrowband IoT we have 9 plus 4, 13 agents. Here in ultra reliable low latency communications, we have only 2 agents. Number of CTU selection and the repetition value. Only 2 agents here we are going to have. So with these 2 agents, so the reward, number of successfully served user equipments, so they have to meet the latency constraint. So the goal of each agent is to maximize the long-term reward. So again, so here the weight matrix theta. So here, as I mentioned earlier, the Q learning table is replaced by the neural network. So here we have the weight matrix, the theta. So the weight matrix is updated, theta t updated to theta t plus 1 by using the stochastic gradient descent method. So every time interval, the weight matrix theta is updated, similar to earlier case. So here, as I mentioned earlier, so the objective of the neural network is to minimize the loss function. So the target minus predicted. So this one similar to earlier. So here we have expected target and the prediction. This is the stochastic gradient descent. So this is the loss function, change in loss function. So as I mentioned earlier, so this DQN, so we decoupled into target Q network and primary Q network. So to solve the overestimation problem, then here the primary network is going to make the decision exploration and exploitation. This is exploitation. So it takes the action that maximize the Q value. So 10% of the time, agent will take the random action, normally 10% or less than 10%. So it is going to take the random action that is called exploration. So here 2 agents. agent 1 and agent 2. These are the observations. Then you get the reward. The reward is fed back to update the DNQ agents, the neural network weights. Okay, so now, we see how we meet the latency constraint. So here we have the latency constraint of 2 millisecond and 8 millisecond we have. So if you have 2 millisecond, if a device does not meet the 2 millisecond latency constraint, it is assumed that its packet failed. So then the two agents, one agent is going to select the repetition value, this one. So that agent can select one of these value, action. So agent can select 1, calculate the Q value. Select 2, calculate the Q value. 4, calculate the Q value iteratively. 6, 8. So which repetition give high Q value, take that action. So similarly, other agent is going to select the CTU number 12, calculate Q. 24, 36. So which CTU number gives high Q value, select that action at the beginning of each transition time interval. So one agent for here, another agent is here. This is the latency constraint. So we consider burst traffic. So here, user equipment 20,000 user equipment. Transmission time interval 0.125 millisecond. So traffic we model for 2 seconds. So 2 seconds divided by 0.125 time slots. The 2 seconds every time TTI, transmission time 0.125. So therefore so you can find how many TTI. So 2 seconds divided by 0.125 millisecond. So now, so that is 2000 millisecond divided by 0.125 millisecond. So now, path loss exponent, transmission power, noise power, SINR threshold. From the base station, we have all devices in 10 kilometer radius. So with these parameters, so these are the machine learning parameters. So learning rate, yesterday we considered different learning rate. If the learning rate is high, it can converge quickly, but non-optimal reward. So if it learning rate low, it takes convergence long time. So learning rate, here we take, this is the normal one. So then memory size, discount factor, so mini batch size to update the neural network. So this target Q network updating frequency, I mentioned theta bar, approximated theta after every 1000 iterations. So with this one, so here the neural network, each layer the nodes 128 rectified linear units. So these are the results we got here. For K repetition factor and the proactive factor. If you take the number of successfully served user equipments under proactive scheme is 1.5 times more than the repetition scheme. So here you can see the red line. So if you see the red line, here roughly 10, here roughly 15 during the burst scenario, because the reason is the repetition scheme will not meet the latency constraint. Latency constraint 2 milliseconds. So if it does not meet the 2 milliseconds, it's failed. So that's what, but proactive, it can meet the latency constraint because it terminates before the end of the last repetition. But the K repetition scheme, it will have to wait till the end. So it won't meet the constraint because this is constraint, there's a constraint there, latency constraint. So K repetition scheme will not meet the latency constraint. So that's what the performance is better. Now we can see here, so this one is fixed value. The green line is fixed. So fixed means number of CTU fixed 48, repetition fixed to 8. So green is fixed. So the bursty traffic, the number of devices, active devices increases suddenly, but fixed means we fix the CTU only 48 available. We are not going to change it. Repetition fixed 8. So then other one is load estimation. In the load estimation, we fix the repetition K is 8. So when you see here, number of successfully served devices, you can see the green one, fixed one completely failed. Fixed one completely failed. So the black one is the multi-agent DQ network not collided here. So that is, say here you will see that during the bursty traffic all fail, but this black one, the dynamically changing, much better than the other schemes here. So here in the proactive, this is in the K repetition scheme. In the proactive scheme, so the fixed one completely failed. So others better because they meet the latency constraint here. Here they won't meet the latency constraint because it will have to wait till the 8th repetition. So latency constraint fails. So this is how the repetition value vary. So here the repetition value fixed 8. Here repetition value fixed 8. Here fixed. So here load estimation. So here the repetition value decreases. Here repetition value decreases. By decreasing the repetition value, it can accommodate more users during the bursty period here. So here CTU number fixed. CTU number fixed. So here CTU number the dynamically changing here. Because here if you have the fixed one, say here 848. So by that way, so we may not be able to meet the bursty traffic scenario. So here basically we have two agents. So the two agents dynamically changing, but we found that so the K repetition scheme will not meet the latency constraint, but proactive can meet the latency constraint. So that's what proactive scheme is better than the K repetition scheme. Now, here we haven't considered multiple configuration grant. Here we have only single configuration grant. But to reduce the latency further, so here if you are interested, you can refer this paper, this year ICC, and this TCOM paper, it will appear early next year. So the full technical details are available in these papers. Now, the thing is multiple configuration grant, because that is the one can reduce the latency further. That is the one is in the standard now, in 5G standard. So if you have multiple configuration grant, we are going to have the same problem. One more agent we are going to have. Because same problem, one agent to select the CTU number, other agent to select the repetition value. Now we are going to have one more agent, which configuration is better. So we are going to have multiple configuration. So we are going to see which configuration is better. here the problem is how to select the multiple configuration grant. So we have to meet the reliability constraint, latency constraint, and we have to how to balance the allocation of channel resources among multiple configuration grant we are going to see here. So now here, these are the different scenarios we are going to have. So here we have the configuration grant and repetition, number of CTU. Here three parameters here we have. 3 agents, 3 parameters. 3 parameters are number of CTU, repetition value, the number of configuration grant. So if you take, these are example. This is one configuration grant, one possibility. So here you have 2 configuration grant, first row, second row, 2 configuration grant. 2 CTU, first row, second row, 2 CTU. Then here we have the starting only at this time. So this is one configuration grant. Repetition 4. Say here if you take this configuration grant, so here we have CTU, 3 CTU for example. This is 1 CTU, another CTU here. Here we have the configuration starting time 2. Repetition here 2. Here repetition 3. Here repetition 4. Here repetition 1. Here starting slot from 2. Here starting slot 1. Starting slot 0. Starting slot 3. So here these are the examples for number of CTU, number of repetition and the starting slot. So now the question is, so here which starting slot is better? So that one also have to select. So we are going to have same as earlier. Here we are going to have one more agent we are going to have. So which starting slot would be better? Same like earlier. So now here you have, so base station configuration for uplink. So base station will have to select 3 parameters. So that is, what is the repetition, suitable repetition value? What is the number of CTU? What should be the best starting time slot? So here the base station, so here it decodes each repetition independently. So here in this work we consider K repetition scheme, not the proactive scheme. So here we consider the K repetition scheme. So again the observation same. Again observation same. So the number of idle CU, collided CDU, then singleton CTU, again observation same. Then number of user equipments successfully detected and decoded. So number of user equipment successfully detected but not decoded. So with these 5 observations, so here we have one more agent. Earlier we had this first agent and the third agent. Now we have one more agent. So that agent dynamically tell to the user equipment, okay, this starting slot is better because the user equipment packet will arrive at a different time slot. So according to that, you select this configuration. So therefore, these 3 agents cooperatively maximize the number of devices successfully served. Same reward like earlier. So observation same, the reward same. Now here in the action, so we have one more agent to select the starting slot in the configuration. So here the parameters are same. So here this agent, this now we have new agent. So this new agent, so here it will select, it will calculate the Q value for 0 starting slot, 1, 2, 3, 4. Which one gives maximum Q value? It select that time slot. So here number of CTU, 1, 2, 3, 4, 5, 6, 7. So it will calculate the Q value for this 7 CTU, which number give maximum reward, it's like that. So here we have the cell radius 10, number of devices 10,000, 50,000. So here the traffic duration we consider 1,000. Again we consider the base station and located at the center of the 10 kilometer radius area. So here we consider, like earlier, 3 hidden layers with 128 rectified unit. So now we see the performance. So here we have low traffic scenario. So in the bursty traffic modeling, we learned 2 scenarios. One is low traffic and heavy traffic. So the heavy traffic is, the peak is very high. The low traffic is, peak is not that high. It's still bursty, not. So here we considered the beta, time limited beta distribution. So, and we see single configuration grant and multiple configuration grant. If you see with this time limited beta distribution, 30, 40, and here we have 3, 4. So when we take single configuration grant, here the black one, so completely failed when this beta distribution here, number of successfully devices during the bursty period is low. But in this distribution, so red and green, multiple configuration grant here for this distribution, and this one blue and green, sorry, red. So here green and red for beta distribution 3 and 4, single configuration grant, and the multiple configuration grant, same performance, because here the parameters 3, 4 is not too bursty here, but here we have the bursty traffic is very high value. So here you can see it is too narrow, so that means bursty during a very short period of time. Here you can see it a little bit wider, the distribution 3, 4. So when you take the high traffic scenario, so for whatever value distribution, so single configuration grant completely failed. Single configuration grant completely failed. The reason is, so it won't meet the latency constraint. If you have single configuration grant, it will have to wait till the beginning of next frame. So the latency constraint it won't meet. So now when you take here latency, so here when you have multiple configuration grant, this red and blue, the latency is less than 1 millisecond. So that is what needed. So that's what in the 5G standard they proposed multiple configuration grant. Then only the requirement in 5G, 6G, the ultra reliable latency communication, the layer should be less than 1 millisecond. So that's what they proposed, this multiple configuration grant in release 16. Even if they proposed multiple configuration grant, if you don't optimize dynamically, you won't solve the problem under bursty traffic. So in the standard, no machine learning, but you have to use the machine learning to dynamically change the parameters, 3 parameters at the beginning of each transmission time interval. Then only we can achieve the 1 milli less than. If you have single configuration grant, so latency is nearly 2 milliseconds. Here this is less than 1 millisecond. So again, here we considered the number of idle CTU. So here the in the multiple configuration grant, different traffic. So the high traffic and low traffic. So in the low traffic is the idle is almost same for single configuration grant multiple, but for high traffic, so single configuration grant, the number of idle is this one, and number of idle here in multiple configuration grant, it is higher. So now here you can see the effect of multiple configuration grant. So here multiple configuration grant 2, 3, 4, 5. So multiple configuration grant, so the red one. So red one, so if you have more multiple configuration grant, you can, the performance is higher, latency lower. So here you can see red line. So multiple configuration grant successfully serve as many servers as possible during the bursty traffic while achieving the latency is less than 1 millisecond. So therefore, the conclusion is for the new use case of massive ultra reliable low latency communication, so multiple configuration grant already is in the standard. So that is, you are going to use the repetition scheme with multiple configuration grant. So the grant free, so you can achieve 1 millisecond, but that is not for bursty traffic. So for bursty traffic, the solution is we have to use the machine learning. Then only we can meet this requirement. If it is not bursty traffic, it is fine. So not bursty traffic, so then the machine learning is not necessary. So, but in practical scenario, we are going to have time to time, we are going to have bursty traffic scenario. So the only solution is we are going to have machine learning agents at the base station dynamically change the parameters such that they can meet the requirement. Okay, so from that topic, so I selected the machine learning part and here presented. So now we are going to have, so I haven't given the slides, but I can share the slides. So after the break, so then I can give some introduction about federated learning, because from 2017, last 5 years, after the Google proposed the idea of federated learning, so the last 5 years, the federated learning is the hot topic in machine learning. So many work have been done in the area of computer science. So only recently, last 3-4 years, 2019 onwards, last 3 years, there are many works on in wireless communication. So after the break, I can give you an introduction about federated learning, and we have done some works on federated learning for wireless network, but those papers are under revision, journal paper. So I can quickly provide some outline of the recent our work. But there are many works in wireless communications in using federated learning. So after the break, I can give, but I can share the slides. I can give it to Prabhat. He can share with you by email. To give the email to him, he can share the slides because I haven't sent the slides earlier because I don't know how many hours. So that's what I didn't share the slides earlier. But after this, I can select and send the slides of federated learning. So after the break, 1 hour, if you learn, if I introduce federated learning, so you will get a rough idea. So how the research work on future wireless communication evolve. Okay, we can have the break and come back.
Yesterday I was discussing with you.
Yeah. So once I go back, I can ask my student.
I have to discuss that if you remove that.
Huh?
If you remove that mic, I will answer also. So,
Because all courses are with my students.
I will-
My paper here, not that one. That why you say can leave. Why leave is a lady, not your lady. Can leave. The lady now is China. Why leave? Why leave? There are John the